All right. This is Jonathan Gardner. I've been lazy and haven't been able to make videos the usual way. So I wanted to cover introduction to physics. There's a number of good textbooks out there that you can study on your own, or with somebody, or if you're taking an introduction to physics class, this would be something that you would see here. This book is special because if we go to the copyright page, you can see it says no rights reserved. Any part of this work may be reproduced, transmitted, shared, stored, or used in any form or by any means, graphic, electronic, or mechanical, including and not limited to photocopying, recording, scanning, digitizing, taping, web distribution, information networks, or information storage and retrieval systems without the prior written permission of the publisher. So this version of the book is 100%. I can distribute a PDF of this. You can download it. There's absolutely no limits. This is the 9th edition. There's been subsequent editions with significantly stricter copyright restrictions on this. So this is the one I'm planning on using simply because it's available and it's free. And I don't see, if you're going to be watching my videos to study physics, investing in this kind of book is excessive. It's way too much. It's just, if you're taking a university course and you're already spending money on tuition and you plan on being a serious physicist, then obviously you're going to buy the book. And I would hope you would keep the book for future reference as well. But anyway, that's the big reason why I want to use this book. Now, as with any physics textbooks, there's a section that I think you should read carefully to the student. Physics, like mathematics and other hard science courses, is a contact sport. So you have to get dirty. You have to do the work. And part of the study is learning how to study this kind of subject, right? And the recommendation is that you read the chapter or section before the lecture, right? You take notes. If you have any questions about the material, you write down your questions. See if you can get them answered before the lecture. There's quick quizzes in this book that might help you kind of gauge how you're doing. I think there's answers to quick quizzes in the back. Let me double check. Yeah, there's answers to quick quizzes and the odd numbered problems. So you can use that as kind of a barometer about whether or not you're successfully understanding the material, right? Having a regular study schedule, preferably a daily one, just like exercising your physical body, your mental faculties need to be exercised constantly. And if you try to cram before a test, or if you try to shove everything into a single day, you're not going to get as much out of it as versus studying it, 1 hour a day or 30 minutes a day or something. So schedule a time, set that aside, and consistently approach the problem. Problem solving. So I'm just going to read this here. Richard Feynman, Nobel laureate in physics, once said, You do not know anything until you have practiced. In keeping with this statement, we strongly advise you to develop the skills necessary to solve a wide range of problems. Your ability to solve problems will be one of the main tests of your knowledge of physics. Therefore, you should try to solve as many problems as possible. It is essential that you understand basic concepts and principles before attempting to solve problems. Okay, let me just repeat that. Don't try to solve the problems until you've understood the basic concepts and principles around the problem. You're wasting your time, or worse, you could be reinforcing bad habits. You could solve the problem or think you solved the problem, but really you're not doing the right thing. It is good practice to try and find alternate solutions to the same problem. Okay, just because you found a solution doesn't mean you truly understand the material. There's usually more than one way to do this, and finding the other ways or alternative ways to do it is good, because there might be a better way to solve the problem that you didn't know about, or better yet, you might be able to understand that you're lacking in a certain area. And hopefully the problems in this book are pretty good. I haven't done them myself, but judging by the quality of this textbook, I imagine they're pretty good. I did look at a few problems. Here's an example. For example, you can solve problems in mechanics using Newton's laws, but very often an alternative method that draws on energy considerations is more direct, right? So certain problems are much easier to solve when you look at things in terms of energy versus forces and accelerations and stuff. You should not deceive yourself into thinking that you understand a problem merely because you have seen it solved in class. Oh my goodness, this is so important. So for my videos, go back in time. I tend not to show you how to solve particular problems because once you understand how that problem is solved, or how I solved that problem, or how the textbook solved that problem, you've deprived yourself of the ability to learn how to solve problems, right? You have to do this on your own. So just because you've seen someone solve the problem doesn't mean you actually understand the problem, doesn't mean you've developed those problem-solving skills. You must do this on your own. The approach to solving problems should be carefully planned, okay? And there's a, read through this section, there's a systematic way to solve problems and apply that strategy and get good at it, okay? All right, so, this physics is a science based on experimental observation. So ultimately, we're going to talk a lot about theories. We're going to talk a lot about math. We're going to solve a lot of problems, and I'm going to use my finger quotes, problems. But mostly what physics is, and what I think of physics as, and what most physicists think of physics as, is an actual practical approach to understanding how the world actually works around us by experimentation with the actual world, right? And so if you go through this from a purely theoretical approach and you don't actually try any of the experiments on your own, you're going to be missing out on what I feel is the more important part of physics, is actually seeing that these things actually work in real life, you know. With that out of the way, I'm going to quickly go over the organization of the material here. And they have this book divided into 5 or 6 parts. Yeah, 6 parts. The first part is called Mechanics. Mechanics deals with how things move. Okay, it's not about gears and gearboxes. That's a small part of mechanics. But when we physicists talk about mechanics, it's how things move. Oh, I should probably preface this with this textbook, and all textbooks like this textbook are not physics. We're getting you familiar with the language of physics and what we're actually doing. But the rigor of physics is not present here. The actual physics that was done by Newton and others that have gone before us, it's only glossed over. Like, we're just teaching you, like, these are the words that we use and these are what these words mean, so that when you go back and when you read other papers and when you start doing actual physics, you have some kind of frame of reference to understand what's going on. So mechanics has to do with how things move, right? Oscillations and mechanical waves. This is a different kind of motion that's pretty important, not just for mechanical things like physical matter, but also it has to do with quantum mechanics and all that kind of stuff. Thermodynamics. This is the understanding of what temperature actually is. That's thermo, and how that changes. Dynamics is something is changing and understanding how it changes and how it evolves over time. Electricity and magnetism. I think that's fairly self-explanatory. It's not focused on electronics. It's more focused on what's actually going on inside of electronics. Light and optics, a very, very important and interesting topic. One of my favorite topics, actually. This section was a lot of fun because a lot of the physics here is very geometric and not so much like we're going to solve equations. It's pretty fun stuff. And then modern physics. And modern physics is basically everything else. It's just miscellaneous. So modern physics covers relativity, quantum physics, quantum mechanics, atomic physics, how atoms work, molecules and solids, nuclear structures, and nuclear physics, and some particle physics and cosmology. So just some interesting little things that, well, I say little, they're really not, these aren't really little topics, but this is more like what we're interested in nowadays. So anyway, each of these parts is super important. I don't know how your university breaks these things into sections, but I certainly recommend that you take a part and study it intensely. And then at the end of that part, basically review everything you've learned, build up for yourself like a notebook of formula and principles and things that you've learned. Really master a part before you approach a second part. Kind of use that as what you might call a semester or a quarter of the year as a guidepost for what you're doing, right? I do intend for these lectures to be about 45 minutes long. So with that, let's get started. We were about 10 minutes in. So let's study mechanics. We're going to probably cover chapter 1 here. Physics is the most fundamental physical science is concerned with fundamental principles of the universe. So physics, the physical science. The physics is short for physical science. It used to be called a long time ago philosophy, right? Because a long time ago, philosophy was not just the study of what is true, how do we know something's true, and, what is the nature of reality itself. But philosophy used to be like, how do things move and how do they interact? Kind of like the predecessor to chemistry was alchemy. The predecessor to physics was philosophy. So people had ideas about why things fall, why things stop rolling, and stuff like that. But we call it a physical science because it deals with the physical world all around you that you can see and touch, right? And physics really is probably the most fundamental science course there is, because we deal with everything and we try to understand at the most basic possible level to understand what's really going on. Right. And so all the other sciences, ultimately, when you ask why is that? Why is that? Why is that? You end up at physics. You end up with something having to do with a topic that we cover in depth, So if you're a chemistry student and you're like, well, why does oxygen do that? Why does it do this? Why does it do that? Eventually you're going to end up with the answer like, oh, that's quantum mechanics, and quantum mechanics is based on these principles and stuff like that. And that's physics, So you end up in physics when you ask questions about stuff. And so he divides them into 6 main areas. Classical mechanics, that's basically Newtonian mechanics. Relativity, probably familiar with Albert Einstein and his theory of relativity. I would probably put the word special relativity in front of this as opposed to general relativity. Special relativity has to do with things that are moving very fast, close to the speed of light, whereas general relativity has to do with the structure of the universe, how gravity actually works. And, like space-time curving. That's general relativity. The third area is thermodynamics, heat, work, temperature. Thermodynamics is kind of weird because it's such an old field. And the way that we approach the problems in thermodynamics are very different than other physics. You know what I mean? It's a very well-developed field. And it kind of combines kind of like how algebra and geometry were joined together with, Cartesian coordinates. Now you can write equations for the circle and stuff like that. Thermodynamics brings together these really big ideas and combines them with now we know that atoms exist and molecules and all that kind of stuff. So it's pretty interesting. There's a lot of really interesting stuff here. And this textbook cannot do it justice. It just kind of touches on the surface of it. Any good physics course is going to require that all the physics students study thermodynamics for at least a year. Electromagnetism, again, this is a huge topic. If you don't know what electricity is, what magnetism really is, welcome to the club, right? I remember I was not exposed to electromagnetism in high school, and I went to college and they started saying, well, a charge, interacts with another charge. And I raised my head. I said, what's a charge? And the professor said, that's a great question. Anyway, as you could see by this equation, so he basically ignored it. I asked him at the office. I said, what's charge? He says, we don't know. It's some fundamental property of matter, but nobody really knows what it is, But anyway, so electromagnetism has to do with, how charges behave. Optics, light, very interesting stuff in optics, and quantum mechanics. And we could probably add, probably general relativity would be added to this. And then I would break out particle physics separate from quantum mechanics. And there's maybe one or two solid state physics, or there might be some other areas too that might be interesting, but are mostly unknown outside of physics itself, right? The other thing that's important is around 1900, and he mentions this here, is, physics was we felt that physics was pretty much solved by 1900, but after 1900, everything changed, right? And so we have classical physics is another word for what was going on before the 1900s, and modern physics is everything afterwards. And so I like to use the word Newtonian mechanics because what really is going on is Newton wrote down some equations, and we basically have been using that up until about the 1900s. And after that, then we discovered that that's not a complete description of the universe. There's other things going on, right? So that's kind of a broad scope of what physics is. And we're just going to be covering in this part one a fraction of classical mechanics, right? So part one and part two is classical mechanics. There's so much more to talk about with classical mechanics. We're not going to talk about it. We're just going to cover what this book covers. Hopefully it might mention like, hey, there's some other interesting things happening out there. Okay, chapter one. Okay. Welcome to physics. This is the first lecture. And today we're going to learn about measurement, right? I can blather on and on about measurement, how important it is, right? So, one of the main reasons, one of the questions that we ask ourselves as physicists is, what is real, right? When do we consider something actually physics, and when do we consider it some philosophical or religious or, imaginary, and the answer is really easy. If you can measure it, it's real. If you can't measure it, it's not real. Right. And that's basically the rule, is if we have a way to measure something, then it's real. So when you measure something, you get some kind of number usually. It could be a positive or negative test too, right? But you get some kind of number, right? Like you might measure the length of something, and then you can measure like how fast something is moving, how its length or distance from a certain point is changing over time, right? And then we have these equations that we use that describe how the measurements should change, right? And we can do experiments, and see how the measurements actually change, right? And hopefully, if the theory is any good, it should match, like the predicted results should appear, right? And of course, when you're measuring something, there's always some kind of error. Like no ruler is perfect. Like if you're using your eyeball to look at something and you're like, well, is that 1 1/4 inches, or is that 1 3/8 inches? Or is it actually, 5/16? Or, you can't, if we use a microscope and we zoom in and like, exactly how long is this? And it could be different based on the time of day. Maybe the humidity might even change, the length of the object. And so we really can't measure things precisely. There's always some kind of error, right? Okay. And we talked about Newton a little bit. I cannot emphasize enough how important Newton is for developing physics as a science, right? Up until Newton and the introduction of calculus, physics was more of a philosophical, abstract concept, and some of the stuff in thermodynamics happened before Newton. Some of it came later. But once Newton started writing down those equations or describing how things behave, and how not just the motion of planets, but how it also describes motions of objects on Earth, that was kind of the ball that got things rolling, right? And then at the end of the 18th century, the 19th century, right? So 1800s, that's when electromagnetism and thermodynamics really became mature. It became solid. We pinned things down. We started getting predictable, obvious results that matched observations, right? But in the 1900s, things started changing because people started to notice that those theories weren't complete. They weren't actually describing stuff that was actually happening. Newton suspected that light was a type of particle, but there were some early experiments in his time that showed that light is not a particle. It's actually a wave. So, but later on with quantum mechanics, we discovered that things don't quite behave so clearly. And All right, so let's talk about here 1.1.1, standards of length, mass, and time. So the length, mass, and time are three of the most fundamental measurements you'll ever make. So when you're measuring something, you need a standard, right? That standard has to be consistent, has to be objective, right? Has to be something that everybody can point to and say, that is the standard, right? The way things used to be measured is like if you're building a house, for instance, and you wanted everything to fit together, either they just kind of eyeballed it and just cut things to length. Like we need a board that goes from here to here, and you just cut it to length. But if you had some kind of engineering going on, or people using math to describe things, then people would set a standard. They would say, for this building site, this is what 1 foot is, and they'd use like a stick or something. And then everybody would measure from that stick, right? Which is great for if you're building a building, but it doesn't work if you want to describe all kinds of different things from different realms. And that's one of the reasons why we have so many different systems of measurement. Is it's easy to measure certain things in certain realms, and outside of those realms, it's no longer easy to use those things. So you want to use a different system of measurement, right? So unifying everything together, like how do you unify a mile and an inch? How do you say that a mile is such and such as many inches? It's not really an easy thing, because you can't go out there with like your finger or whatever and start like counting how many fingers a mile is, so it has to be a different way to do that, right? So we use, it's called the SI, System International, I guess Système International. It's French. SI system is the universal standard that we use for measurement. And you might have heard that the Americans, like we're using inches and feet and stuff like that. It's not actually true. The inch is defined to be 2.54 centimeters exactly, right? So we're actually based on SI, right? Everything that we use in the U.S. is based on SI. So we might use different names for the units, and they're different, obviously, but it's all based on the SI system, right? So if I tell you something in inches, you can multiply by 2.54, you get the exact number of centimeters, right? Anyway, so the fundamental units of length. So these are the things that we base everything else off of. So distance is based on the meter. Mass, not weight, mass is based off of the kilogram, and time is based off of the second, right? So we define everything else in relation to that, right? So an hour is 3,600 seconds, as long as there's no leap seconds in there. Then we have like, picoseconds and microseconds. We have, grams and whatever unit of measurement you're going to use. Pounds, if you're using it as a system of mass, inches, feet, it's all based off of the meter, right? So we have some way of saying this is 1 meter, this is 1 kilogram, and this is 1 second. We have some system of doing that, okay? And then you're going to hear about other units, like for instance, in temperature, we might talk about Kelvin, right? We might use in electrodynamics, we talk about amperes, amps. Maybe in optics, you might hear about the candela, and in chemistry, we might hear about the mole. Okay, but all of these things are also defined by the SI. They have a very definite definition. It's objective. Everybody agrees on what it is. There's no argument, right? So let's talk about length. Okay. The meter, some people think it's like some magical number. It's supposed to be a 10 millionth of the distance from the equator to the North Pole, and then a line that passes through Paris. They didn't quite get it right. It was close, but it wasn't quite right. For the longest time, there was a specific bar of metal that was the meter, right? And so other countries, since you can't just walk in there and look at that and say, is this thing a meter long? France, the SI would produce copies of that bar and send them off to different countries. And then those countries could make copies of that bar, and so on and so forth. And that's pretty accurate, but it's not accurate enough, right? And so in the 60s and 70s, they redefined the meter as a certain number of wavelengths of orange-red light emitted from a Krypton 86 lamp, right? And in 1983, the meter was defined as a distance traveled by light in a vacuum during a time of 1,299,792,458. We just say 300 million as a nice round number. But it's a distance that light travels in a vacuum in that amount of time. Okay. And so the length is not an independent unit. It depends on how long a second is, right? It also depends on how light behaves in a vacuum. But since light behaves in a vacuum the same everywhere, that thing is safe and sound. But the question is, what's a second, right? But anyway, so the speed of light is exactly 299,792,458 meters per second, right? It's an exact number, okay? And because we've defined it this way, nobody needs a bar of metal in France or a copy of that bar of metal or anything like that, right? So anyway, let's go to table 1.1. Let's look at some different lengths. So let's start in the middle here. 9 times 10 to the 1. So if you're familiar with standard notation, so 10 to the 1, that's 10 to the first power, that's just 10, right? So 9.1 times 10, so that's 91 meters. 91 meters is the length of a football field. That's about 100 yards, right? Housefly, you might be familiar with the housefly. So this is 5 times 10 to the minus 3. So what does 10 to the minus 3 mean? Well, negative exponents means you're dividing that many times by that number, right? So it's 5 divided by 10 divided by 10 divided by 10, right? So 0.005, right? So 0.005 meters, we would say 5 millimeters, right? Is about the size of a housefly, okay? The smallest dust particle ever is about 1/10 of a millimeter. So it's 10 to the negative 4, so 1 divided by 10 divided by 10 divided by 10 divided by 10. Right, so 0.0001 meters, or 1/10 of a millimeter, is about the smallest dust particles you can see, right? Cells are pretty dang small. They're 1 divided by 10 5 times, which is 100th. No, hold on. 0.00001. So it's 0.01 millimeters, in which case I think 10 microns. Is that correct? Microns? Don't quote me on that. We'll talk about that in a second. And then 10 to the negative 10, the diameter of a hydrogen atom, very, very small. Okay. And then if you divide by 10 4 more times, you get the diameter of an atomic nucleus. So the size of the nucleus, the inside of an atom, is 1/1000th. No, 1/10,000th. The size of the atom, right? So the nucleus is extremely tiny. And then inside the nucleus, 10 times smaller than that is a proton, right? And a proton, I think, is about the smallest thing that has measurable size, right? You can't really get much smaller than that, okay? And let's go bigger than a football field. If we have 2 times 10 to the 5th, so that's 200,000. So 200,000 meters, right? Or we would say 200 kilometers, right? That's the altitude of a satellite orbiting the Earth, okay? And then 6.37 times 10 to the 6, so that'd be 6.37 times 1 million. So 6.37 million meters is the mean radius of the Earth. So that's the average mean. In this case, doesn't mean like it's being angry and treating people unfairly. No, that means it's the average radius of the Earth is about 6.37 million meters. So 6,370 kilometers. The distance from the equator to the North Pole is about 1 times 10 to the 7th, so 10 million meters, right? Okay, and then the mean distance from the Earth to the Moon, 3.84 times 10 to the 8th. So, what is 10 to the 8th? That's 100 million. So 384 million meters. And then the distance, orbit radius of the Earth about the Sun, I believe that's from the center of the sun, not the surface of the sun. Not that it'd make much difference, but that's 10 to the 11. So 11 zeros, or actually 1.50 times 1 with 11 zeros. That's a big number. Anyway, these numbers get really big really fast. So multiply that by 10,000, you get 1 light year. Multiply that by 10 more, and you get the distance from the sun to the nearest star, Proxima Centauri. So it's about 10 years light takes to travel from Proxima Centauri to our solar system. And the nearest large galaxy is 6 more zeros after that. So what is that? That's another million. So 10 million light years away is Andromeda. And then 1,000 times that, so 3 more zeros, is the Earth to the most remote normal galaxies. And then with the distance from the Earth to the most remote known quasar is this astronomically huge number, 10 to the 26 meters, right? And that's meters. That's distance, right? So a meter is, let's see, I think 2 meters, somewhere around 2 meters is like the height of a human. A meter's about 3 feet, right? A yard and a meter are somewhat comparable. Not exact, but close, right? Anyway, mass. Let's talk about mass. How am I doing on time? The fundamental unit of mass is the kilogram, not the gram. Okay, it is defined as the mass of a specific platinum iridium alloy cylinder kept at the International Bureau of Weights and Measures in Sevres, France. Okay, I think like within the last few years, and I think the physics guy on YouTube covered this. It has been redefined as, the mass of a certain sphere of a certain radius of a certain material. And what is it? Veritasium, I think, has a video on the new definition of the mass, right? But the mass, for the longest time, we could only say like this block of metal is 1 kilogram, right? And so you would get a scale that would, tell you if something is the same mass as something else, and you would carefully measure another mass and say that they're about the same mass, right? And then use that, for the U.S., and the U.S. can do their stuff, right? So let's talk about masses. So let's see, 10 to the 2. So 100 kilograms is about how much you weigh, right? 1,000 kilograms is a shark. I assume they mean like a great white shark, not like the small sharks that are in there. The moon has a mass of 10 to the 22. So that's a very large number, right? Earth is 10 to the 24, 100 times the mass of the moon. And the sun is, it's 6 more zeros at the end. So it's 100,000, a million times the mass of the Earth. So 1 million Earths is about 1 sun, right? And then the galaxy, all the objects within the galaxy is 12 more zeros behind the mass of the sun. I don't even know what number that is. That's too big. And everything in the observable universe is 10 zeros. So you have like 10 billion Milky Way galaxies makes up everything that we can see in the universe. So 10 to the 52. That's a large number. But a frog is about 1/10 of a kilogram. A mosquito is 1/10,000ths or 100,000ths. Let me think. 1, 2, 3, 4, 5. 100,000ths of a kilogram, right? A bacterium is, very small, 10 to the minus 15. So that's a 0.00014 times 1, right? Kilogram. And then a hydrogen atom is way smaller than that, 10 to the negative 27. And an electron has a mass of 10 to the minus 31. Okay. Time. Before 1967, the standard time was in terms of the mean solar day, right? And so a solar day, so you basically point at the sun, and then you wait until the sun goes back to that point, right? It's not the most accurate way to measure time because we've discovered that not every day has the same length, There's different reasons for that, but so they said the average solar day, because some days are a little bit longer than other days, right? And the second was, 24 hours in a day, 24 hours in a day, 60 minutes in an hour, and 60 seconds in a minute. So that was not a very good way to measure time, because we found out later that the Earth wasn't consistent, and 1 year or the next year could be a little bit longer, a little bit shorter, right? In 1967, we started using atomic clocks. I think this is a picture. Nope, that's the standard kilogram. I think this is actually the atomic clock, yeah. And there was a guy on YouTube experimenting with these things. These are not easy devices to keep running. Atomic clock, which measures the vibrations of cesium atoms. 1 second is now defined as 91926317770 times the period of vibration of radiation from the cesium-133 atom. Okay, so they get that atom vibrating, or rather material with that atom vibrating, and then they can measure, how many vibrations for a second, right? Extremely accurate. We're able to measure time dilation due to general relativity because of it. So very accurate. Anyway, yeah, well, I'm not going to talk about customer system. Just we need to understand that it's all based off of, the meter, the kilogram, and the second. The multipliers, milli, nano, blah, blah, blah. I think here's a table. This is another table you're going to want to memorize. As a physicist, I can tell you which ones are going to pop up a lot, right? Obviously, centi and milli for millimeters and centimeters, right? Micro, I think a micron is 1 micrometer, I believe. Nano, that appears quite a bit. Nanometers is like light and stuff like that. And then we get to pico and femto. That's, we're talking about distances at the atomic scale, right? So stuff inside of the atom, at pico and femto. I don't know. Nanograms, I think, comes up when we're talking. I think at that point we just use like 10 to the negative 15, because femtograms, we talk about picoseconds and nanoseconds. That's stuff there. Kilogram, obviously, megagram, giga, tera, peta, exa, yada. You're probably familiar with mega, giga, tera in terms of hard drives, but typically hard drives are not, they're not based on the power of 10, but on the power of 2, right? So there's not quite exactly, a million or a billion or a trillion, but it's close, right? You have to kind of read the label of the package on your hard drive to make sure you're getting the right number of bytes. Nowadays, peta and exa are things that we talk about in terms of byte storage. But again, like when the numbers get big, we use the exponential form. That's how we, like 10 to the 15, right? Density, let's talk about density really quick. The density rho, that looks like a P, but you're going to want to learn Greek letters. So go find somebody who teaches Greek and learn how to write the letters of the alphabet, right? There's provided the back end paper of this book. Let's go see if we can find the Greek letters. Not there. There it is. Okay, this is the Greek alphabet. You're going to have to learn this. You just have to learn it, okay? The sooner you learn it, the better. Sooner you learn how to write the letters, the better too, right? Upper and lowercase, right? Alpha, beta, gamma, delta, epsilon, zeta, eta, theta, iota, kappa, lambda, mu. We say mu in English, it's mu, but mu, nu, chi, xi, omicron, p, pi, right? You'll hear p and pi. Rho, sigma, tau, upsilon, upsilon. You might hear it that way. Phi, chi or ki, psi or psi. I've heard chi, phi, chi, psi is what I heard sometimes, and omega, right? And this one it's xi, I think, but some people say xi, right? So one more time: alpha, beta, gamma, delta, epsilon, zeta, eta, theta, theta. We say theta, eta, zeta, eta, theta, iota, kappa, lambda, mu, nu, xi, omicron, pi, pi, not p. You could say p, but it gets confused with the English p. Rho, sigma, tau, or Latin p, I mean. Rho, sigma, tau, upsilon, phi or phi, chi or chi. I think chi is probably more popular. And psi or psi. I've heard people say just psi. They just don't even say the p because it's hard to say. An omega, right? Okay, so that's at the back end point of the textbook, just on the last page there. You're going to have to memorize that. Just memorize it. And okay, back to the lecture, section 1.1. Time, we did that. Okay. Another example of derived quantities density, we use the Greek letter rho, and it's defined as that triple equal says that's the definition of it. It doesn't mean like these things are equal. It means this is what it is. This is the definition. Mass divided by volume, right? So we say, so volume, what's volume? Volume is length times length times length, right? Area is just length times length. There's two of them, but volume is three of them, right? And so we write, if we're using mass units, kilograms in this case, and a length unit, meters, and there's three of them, meters cubed, right? Okay. And just talking about densities, like you can look at different densities and stuff like that. So interesting stuff. Okay. So I am going to take a break here. Just kind of cover what we've talked about so far one more time for those in the back. Physics is a science where we measure the most fundamental things that we can possibly observe. And in order to do so, we rely on measuring things. Measuring means like, how big or how long or how heavy or, all those kind of things. We answer those questions with numbers, and those numbers allow us to express equations that describe the stuff that's happening around us. If the predicted numbers match the actual measurements, then we say the theory's good. Otherwise, the theory's bad. We use the SI system. It's from France to define all of the measurements, right? And so that nobody argues about, what measurements are. It's all based on the SI system. Length, mass, and time are super important. Length we define in terms of the meter. Everything's defined in relation to the meter. Right now, the distance of 1 meter is how much distance light travels in a vacuum. And 299,792,458 seconds, right? So light covers that distance in 1 second, 299,792,458 meters in 1 second. Mass is defined, I think nowadays based on the volume of a certain sphere, but at the time of this book, it was based on a particular lump of metal, right? And then time is based on how many cycles, 9,192,631,770 cycles from the radiation from the cesium-133 atom, right? And we use the prefixes for power of 10, but I'll be honest with you, often we just use the power of 10, unless it's like useful, right? And then we also have derived quantities that are based on the fundamental quantities. Like, for instance, density is mass divided by volume. And volume is, lengths cubed, right? Okay, quick quiz. 1.1. In a machine shop, 2 cams are produced. What's a cam? Well, a cam is you have like a shaft, right? So you have like a long tube, okay? And then a cam is kind of like a protrusion out of that shaft, so that as the shaft rotates, there is a linear translation. So things are moving up and down. Like if you want to like cause a valve to open or close at certain positions on the rotation of that, cylinder, then you have a cam, right? So 2 cams are produced. One is made of aluminum and one is made of iron. Both cams have the same mass. Which cam is bigger? Which one is larger? So when it says larger, it's asking which one takes up more volume, right? And so the question is, does the aluminum cam, is it larger? Does the iron cam is larger, or both cams have the same size? Okay, so take a minute. Ask yourself, before you answer this question, ask yourself, what is the difference between aluminum and iron that's relevant to this problem, right? We're thinking about mass and volume, right? So think about that, and there's a hint here that just talking about this in this paragraph up here. It says aluminum has a density of 2.7 times 10 to the third kilograms per meter cubed, and iron has a density of 7.86 times 10 to the 3 kilograms per meter cubed, right? So which one is more dense, right? So obviously the iron is more dense. It's like 3 times as dense, almost 3 times as dense, right? And then look at the problem again. It says, well, we have 2 cams. One is made of aluminum and one is made of iron. Okay, so they're 2 cams that are different because one has aluminum and iron. The similarity between them is they both have the same mass. Okay, so which one is larger? So if the aluminum cam is larger, what does that mean about the density of the aluminum? Is it higher or lower? If the iron one is larger, is it higher or lower? Okay, I'm not going to answer this for you. I'm just going to give you a chance to think about it, right? And again, you're just comparing these two numbers, 2.70 and 7.86. Somebody just joined. Hi, welcome. I'm recording right now, so. All right. Okay, excellent. That's section 1.1. Section 1.2, matter and model building. If physicists cannot interact with some phenomenon directly, they often imagine a model for a physical system that is related to the phenomenon. Okay, we use models all the time for everything. Okay, we cannot understand directly what's actually going on in the universe. There's just too much, right? And even if we were to perfectly understand the mechanisms that are actually occurring, it would probably be too much detail for us to actually make any kind of reasonable prediction, right? So what a model is, it's a simplification and a simplification that we can actually analyze and look at and understand, right? And so even though a model doesn't directly represent everything that's going on, it gives us a good enough rule of thumb that we can actually make reasonable predictions that come true, right? And so models are like equations or something that describe what's actually going on. Well, it doesn't describe actually what's going on, but describes a simplified version of what's going on in a realistic and effective way. And so they have this paragraph. As an example, consider the behavior of matter, right? And they show up here, they say here you have a bar of gold. And what's gold made of? Well, it's made of gold atoms. If it's not, it's what is it, 99.99% pure or whatever it is, right? So there's probably some silver atoms or maybe something else in there, but mostly it's gold atoms, right? And what's a gold atom? Well, inside of the nucleus, there is a certain number of protons and neutrons, right? So, and then what's inside of the proton? Well, there's some quarks doing some really fancy and amazing stuff, right? And the question is, do we really care about the quarks if we want to know whether we're rich or not, right? Ultimately, it's the amount of gold that we have, right? And so it kind of doesn't matter to us the quarks are there. It doesn't matter to us that gold has a certain atomic number, and it kind of doesn't even matter to us that there's actually atoms inside of that gold bar, right? But there's certain things we might want to do with the gold that requires us thinking about the atoms, right? For instance, when the famous experiment where they were shooting alpha particles at gold leaf, and some of those alpha particles were bouncing back. If you were thinking of gold leaf as just very, very, very thin pieces of gold, just a homogeneous substance, like a soupy mixture, like a rice pudding or something like that, then it doesn't make sense why those alpha particles are coming back to you. But if you realize that they're made of atoms and atoms have these very dense nucleuses, then things make a lot more sense. You're probably thinking of dense nucleuses when you're doing that experiment versus, just a lump of gold. The whole idea of the word atom, that comes from the Greek word atomos, which means you can't cut it. No cutting, right? And so atoms are something that they're the fundamental unit of matter. Now, it's important to realize that this concept has been around for all of recorded history, right? The most earliest manuscripts of philosophy talk about whether or not you can cut matter infinitely into infinitely small pieces. But it wasn't until, I believe it was Einstein's experiment or Einstein's understanding of the Brownian motion. So he published a paper on that. And that's what basically everybody said. Now we're very sure that atoms are real. This is the actual nature of matter, right? So it's very interesting there. Now, J.J. Thomson identified the electron as a charged particle. That was interesting. 1911. This is the experiment I was talking about. They don't talk about the experiment here, but this is actually one of my most favorite experiments here, is that experiment in 1911 when Rutherford detected the alpha particles bouncing off the gold leaf. That was amazing. And now we know that the atoms are separated by their atomic number, mass numbers, blah, 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 all that kind of stuff. Okay. So this is a good point here too. Even if we consider atoms and nuclei, there's some experiments we perform where thinking of them as atoms or nuclei is not enough, and we have to understand that the protons are actually made up of quarks, right? And so those experiments, we kind of don't even consider the gold at all. It's not even important. We're thinking about the quarks and what happens when things interact with those quarks. So this is an example of how, like, we have different models to describe the same thing, and the different models are very useful for where they're useful, and they're not useful for where they're not useful. And there's limits to the models, right? And so you have to understand when you have a model of the universe, you have to understand where things stop working and where things work really well, right? Because every model is a description of the real universe that is not complete, right? There's always problems with every model. So every theory that you learn about in physics is going to have problems in some area, right? Either it's way too complicated for the problem you're trying to solve, or it doesn't give consistent results at certain scales. All right, section 1.3. So we talked about models. This is a very important thing that we do in physics all the time. And what's the right way to describe this? You've probably already seen this in your high school courses when you've talked about math or physics. But okay, let me try to put it to you this way. Sometimes we're trying to understand a physics problem, and we even forget the formula that we're supposed to be using. But we know what the answer is supposed to look like. Like, for instance, the answer is like density. So we know it's mass divided by length cubed, right? That's what the answer is going to look like. And so we have a mass and then we have a volume. We're like, well, how do those two things relate to the density, right? And we're like, well, the mass goes on top and the volume goes on the bottom because we know that it's kilograms divided by meters cubed, right? It sounds really obvious, but it's very effective, especially for more complicated things that we're trying to analyze. And they give an example here. They say that we're going to use brackets to denote dimension of a physical quantity. For example, the symbol used for speed in the book is v. And in our notation, the dimensions of speed are written. And so they're going to use brackets around the v, and they say that's just length divided by time. Okay. And area, the dimensions of area is just length squared. Right. And so here are some fundamental derived quantities from the fundamental units, the fundamental units being length, mass, time, and some other things. And so in dimensional analysis, we might say that the area is just L squared. So expect to see two lengths multiplied together. Volume is L cubed, speed is L divided by T, right? So whatever time unit you're using. And then acceleration is L divided by T squared. So 2 times on the bottom. So for instance, in the standard units, we might see meters squared for area, meters cubed, meters per second, or meters per second square. But in the US, Nobody knows what a meter is, but we know what a foot is, right? So for area, you might hear square feet, cubic feet, feet per second, or feet per second squared. But also, depending on the problem and the scale of things, we might be talking about centimeters per second. We might be talking about, for area, some small areas like picometer squared or something like that, or maybe some large volumes. We might be talking about, light years squared or cubed or whatever, right? So it depends on the area that you're in. You might use specific units for different purposes, but it doesn't change the fact that it's always 2 units of length multiplied together to make area, 3 units to make volume. And he talks about here, you can check to see if you're doing the math right, if you're using the right formula, just using dimensional analysis. So suppose we have the position car at time t, position x of a car at time t, if the car starts at rest x equals and moves the constant acceleration a. The formula we're supposed to use is x equals 1/2 at squared, right? But if we're using the wrong formula, then we're going to see really quickly that the dimensional analysis doesn't pass. So for this formula, x equals 1/2 at squared. So we're going to see a length is, well, what's a? It's acceleration. That's a length divided by time squared. And then we're multiplying by time squared. And so that should give us a length. So that's a correct dimensional analysis, right? And that's a very powerful, tool to use to make sure you're doing things right. You don't have to use any numbers. You just look at the problem and say, well, I know that's length. I know that's length per time squared, and that's time squared. Well, length per time squared times time squared should give you a length, right? Obviously, it won't tell you that, hey, you got to use a 1/2 there, but it'll tell you that you're in the right ballpark. And so we might use this little symbol here. That is proportional to. That's the way you'll hear that, is say it's proportional to. And what that means is, hey, this quantity here and that quantity there are related by some number that we multiply it by. Okay. All too often in physics, we say, hey, it should be this. We don't know what the constant we're going to multiply by is, but this is enough to get the problem started and get us closer to the answer. And yeah, so for instance, because of dimensional analysis, we can instantly recognize that if we have acceleration in time, we want to find how it relates to the position. We can see that it's going to be proportional to acceleration times time squared, not acceleration squared times time or anything like that. Just acceleration times time squared will give us the length. All right, quick quiz 1.2. True or false? Dimensional analysis can give you the numerical value of constants of proportionality that may appear in an algebraic expression. So the question is, using dimensional analysis alone, that's just like examining that the units match for the equation, can we figure out what the value of constants of proportionality? So what does that mean? The constants of proportionality. Well, that means that, like in this case, x is proportional to at squared. Let me go up there. X is proportional to at squared. Can this tell us how x relates to that, right? Like what factor is supposed to be in there? Or does it tell us that there is some factor, we just don't know what it is, right? And so can dimensional analysis tell us what the factors are supposed to be? Okay, true or false? Dimensional analysis can tell you what the constants of proportionality are supposed to be. I'm not going to answer that. That's for you. Okay. Example. Let's go through this example and see how it works. In fact, I think I am actually almost done with time for this lecture. And I was going to allow people to ask questions. What I'm going to do is stop recording here in a few minutes, and then we'll just open it up to discussion. Analysis of an equation. So example 1. Show that the expression v equals at, where v represents speed, a acceleration, and t an instant of time, is dimensionally correct. So we're only interested in the dimensions, right? So we identify the dimensions of v. V is length over time. We identify the dimensions of a. That's length over time squared, right? And the dimensions of a times t, well, we're multiplying by time, so we just get length over time. And since v is length over time and at is length over time, we see that it's dimensionally correct, right? All right. Now, if we did v equals at squared, is that dimensionally correct? Would that work? If we're multiplying L over t squared times t squared, would that give us L over t? And let's do one more here, just for the road. Analysis of a power law, example 1.2. Suppose we are told the acceleration A of a particle moving with uniform speed v at a circle of radius r is proportional to some power of r, say r to the n, and some power of v, say v to the n. Determine the values of n and min and write the simplest form of the equation for the acceleration. So this is a case where you don't know what the formula is. I don't know what the formula, I probably do. I don't remember. And we're just going to see if these things can be brought into some relation, whether it's worth trying to solve a problem and figure it out, right? So we're writing a proportionality expression for A with a dimensionless constant proportional to K. So A is equal to K, that's just some constant, we don't know what it is, times R to the N, V to the M. Okay, so let's substitute in the dimensions. So A is L over T squared, and then we have R, which is a distance. The radius is a distance, right? So L to the N, and then V is length over time, so L over T to the M. And so we multiply that out, we get L to the N plus M over T to the M, right? Because when you multiply L to the N times L to the M, that's just the same as L to the N plus M. That's how exponentials work. So L to the N plus M over T to the M is L T. So we have 1 on the top, 2 on the bottom. So N plus M have to equal 1. And there's a 2, well, M has to equal 2, obviously. So N plus M have to equal 2. We plug in 2 for M, we get N plus 2 has to equal 1. So N has to equal negative 1. Okay, so A is equal to some constant times R to the negative 1 times V to the 2. And so we just move that R to the bottom. So it's K V squared over R. So acceleration is related to the square of the velocity of the object divided by the radius. So we don't know what that proportionally constant is. It kind of doesn't matter in many cases because we know if we double the velocity, the acceleration will be 4 times as much. If we double the radius, then the acceleration will be half as much, right? And indeed, if you go to section 4.4, it'll tell you that the equation is, I believe, K equals 1. So the equation is A equals V squared over R. That's the actual equation. So we got close, right? We got pretty dang close. And in the next lecture, we're going to do probably 1.4, 1.5, 1.6. I think we're going to be able to finish all that. So, and with that, I'm going to stop recording.